Bismillahirrahmanirrahim. Let's first take up the forces taken up by the bolt and the members. And now, before we apply the external load, this P is the external load. Before we apply the external load to any system joined by bolts, we have to first make that a joint, and that is done by tightening the nut. By doing this, we bring these members into compression, and the bolt itself, it goes into tension, and this is how we make a joint. The load is applied later on. So before the application of external load, you have this force in the members, which is compression, and let's call it Fi. Now this is before we have applied the external load here. At the same time as this is applied to the members, the boards experience the same force but tensile, and this is obviously a requirement for equilibrium. Now let's call these preloads. Now after a joint is made by applying these preloads, external load P comes into the picture. You apply the external load. Now by external load I mean the cumulative effect of this, the total force applied on one bolt. Now it could be that your system consists of more than one bolts, and the total load taken by the system is P total, and the number of bolts is N, and you get the external load per bolt by a simple formula like this. Now from here, the immediate goal is to find out the ratio of this P taken up by the bolt and the ratio taken up by the members. Let's define this here. Share of P taken up by the bolt, PM. Share of P taken up by the members. Now one thing we know from the start, that P must be equal to PB plus PM. The two shares must equal the total load P. Now if you want to find out this PB and PM, we need one more equation. This is just one equation. We need another equation, and that equation comes from kinematics, the deflections. What we know in this system is when P is applied, tension in the bolt will increase, compression in the members will decrease. So both will experience a deformation, delta. Now delta in the bolt, which will be extension, will be equal to delta in the members, because the members will now experience less compression that they did before the application of the external load, and this change in length must be equal. Now if that is so, we know the formulas for these. It is very easy to write this delta B and delta M in terms of forces and stiffnesses. Delta B, PB over KB. KB is the stiffness of this bolt. We know how to calculate these. Delta M is similarly force taken by the members divided by Km. Now from this we can equate these two, and we can write PB over KB is equal to PM over KM, or we can write PM in terms of all the other quantities, KM over KB into PB. Now if we put this in the original equation, the equilibrium equation, now P is equal to PB plus KM over KB into PB, or we can write PB, or we can write P is equal to 1 plus Km over KB into PB, which implies that P is equal to KB plus Km over KB into PB. Now we are interested from the start in the share, so we are interested in this quantity, and it is very easy to write this. This simply becomes By simple rearrangement, we can write this force taken up by the bolt, and this is simply by rearranging this. Now, let's define a quantity here and call it joint stiffness constant C, and the quantity is nothing but kb over kb plus km. So if this is our new quantity, then we can write this equation as pb is equal to cp. This is the ratio of load, external load P taken up by the bolt, and since we know that P is equal to PB plus PM, obviously the rest of the load must go to the members, and that means that PM will be 1 minus C into P. So these are the loads taken up by the external loads taken up by the bolt as well as the members. Now recall that before this, before the application of the external load, there was already a load there on the members, and that load was the external load, the preload. Negative in the case of members and positive in the case of the bolts, but of equal magnitude. So the total load on the bolt as well as the member after the application of loads, total loads, that is initial preloads as well as the external loads, it's become FB, because FB was already in compression in tension, and this was the pretension, and here preload, and here you have the load added. As far as the members are concerned, the portion of the external load is this one, but initially it was in compression, so this is the total force in the member. Now these expressions are only valid when Fm is less than 0. That is, the members, the tension or the lessening of the initial compression is not so much that Fm is 0. That is, there is no compression. Because in that case there is no joint. The plates have separated now. So that's not a joint at all. So these are valid only for Fm is less than 0. Now, this expression, it's very clear from this that the denominator must be much higher than the numerator, because this stiffness in the members, member stiffness is much larger than the bolt. So what happens as a result of this is this the C value, this turns out to be, obviously it's different for different cases, but on an average it is around 0.2. That is, which means that the bolt only takes 20% or 20 or 25% of the external load. The rest 75 to 80% goes to the members. That is, the members which are in compression, they are still in compression, but the compression is decreased. So that load goes there to decrease the compression. But as far as the increase of tension of the bolt is concerned, that is very small portion of this external load. Now, we can see this situation, and there are consequences of this, and I'll come to that later on. But before that, I want you to focus on an intuitive way of seeing what is happening. Let's say, because we have to plot both tension and compression on the same diagram, so I'm going to have positive, and here the compression is negative on the same line. And let's say that this is the force axis and these are the displacement axes. Now, a bolt has a stiffness of Kb, which is much less than the stiffness of members. So I'm going to draw this member stiffness line much steeper than the stiffness line for the bolt. Now, when you apply preload, Fi, this much preload is there, let's suppose. what happens is, for this much preload, the displacement, obviously the difference between the stiffnesses means that this is the displacement in the bolt because of the preload. But at this, for the same preload, the displacement in the members is very much less than this. So here we stand before the application of the external load. Now when we apply the external load, these deformations are different. The bolt has been extended much more than the members have been compressed. Now you apply the preload, the external load P. Now after the application of external load, the tension in the bolt will increase, compression in the members will decrease, but the deformation that takes place because of P, it must be the same. This, talking about this must be the same. So now let's say this much deflection is there, and this is positive in both cases. Both the members as well as the bolt will increase in length as a result of the application of loads, external loads. This was not the case in the case of Fi, because in that case one was in tension, the other was in compression. Now let's call this P. This must be equal to the increase of the length of the bolt as a result of external load. But if these are equal, then the forces must be different. This is the portion of load taken by the bolt, whereas this is the portion of load taken by the members, and that is only inevitable because in the initial Fi was the same, the displacements were different. Here in the second stage, when you apply the external loads, the displacements are the same, then the forces must be different. So bulk of the external load, because PP plus PM is P, but this P is much larger than this PP, and this is inevitable because of the change difference in these stiffnesses. So what happens is, as a result of this, the bulk of the moral of the whole story is that the bulk of the external load P is taken up by the members, not the bolt. And roughly speaking, 80% of the external load is taken up by the member, which means that only 20% go to increase the tension in the bolt. Now this has consequences both for static as well as fatigue loading. For static loading, you can use much smaller bolts. Why? Because you apply a loading of Fi, and that is a requirement. You preload all the bolts, but you don't worry about it because you can go very near the material strength, and we'll talk about that later on, what that is. Because you're not worried so much, because you know that even if I go very close to the strength of the material, there's nothing to worry about, because when I apply the load P, most of it is going towards the members anyway. It's not going to increase the tension in the bolt, so I need not worry about that. So I can go to a very high percentage of the strength of the bolt. So you can use smaller bolt size. By smaller bolt size, I mean we can use bolts of small diameter. Now what about fatigue loading? We have a very significant influence or effect of this on fatigue loading as well, because the fact that Fi is there, Fi is already there, it is there. Now when you apply the load P, and it is cyclic in nature, it increases and decreases and increases and decreases. Now this cycle, this amplitude would have been P if all the load was taken by the bolt. But we know that very small portion of this load is taken up by the bolt. The rest goes to the members, and members are in compression anyway. We are not worried about fatigue in members that are compressed. So we are only worried about fatigue in tensile situation. That is the bolt. That is what we are talking about. So the amplitude of P, because most of the P goes to the members anyway, the rest goes to the bolt. So the amplitude of stress is reduced. So the fatigue life increases, and obviously this also in the long run, or if you see the bigger picture, this also then translates into this, because if the amplitude is reduced, then you can use a bolt of a smaller size to withstand the same fatigue situation. Otherwise, if this was not the case, if most of the load was taken up by the bolt and not the members, then you would have been obliged to use the bolts of much larger size. Now this brings us to the end of this particular section, except that we are talking about two types of loading here: initial preloads and the external load. Now these external loads are applied as a result of some sort of cam, or some sort of a linkage, or some sort of a force applied on your assembly. But this Fi, this is applied by tightening the nut. If you recall, this is applied by tightening your nut so that you can have compression in these members and tension here. So how do you relate Fi, which is a force in Newton, say, to tightening of the nut, which is obviously done by some sort of a device which imparts a torque on the nut and the bolt? So this relationship needs to be made clear here, and that is very simple. If Fi is known, and we are assuming that Fi is known, we want to apply this much pretension, and we'll come to this later on when we study the static and fatigue loading. If you know this much preload has to be applied to a nut bolt situation, what kind of torque do you need? Now this is a very simple expression, and this is given in your book, KFID, and here you can take K. If no other data is given, you can take K to be around 0.2 if no data is given, and I'll expand on it later on. Now this D, this is the nominal diameter of the bolt, whatever for M10 it is 10. Now this is a simplification of a very complicated relation, but why we are justified in using a simplified relation is that even that very complicated equation does not necessarily give you the correct answer. And the reason being, if you want to be exact about it, and empirically we have verified this, if you want to be exact about it, there is a table 815 in your book, and that gives you the values for this K for lubricated bolts and non-plated or zinc plated, and there's a lot of detail there, and the range there is from 0.3 to about 0.09 for different situations of material and lubrication. Now if you take this as around 0.1, then the average comes out to be 0.2. So if you know the details of what the situation is, what kind of lubrication is there or not, then you should use these values. But if no such value is given, 0.2 is in between the two extreme, so it gives you a rough figure. Now one thing I need to add here, and that is relying on the torque of a wrench is a very poor indicator of what kind of preload you are applying actually. The best way to do that is to somehow measure the extension in the bolt. If you can do that, that is the most accurate way. But in many cases, you cannot do it, especially when you are talking about fatigue. Then the best way is to somehow find out the extension in the bolt. Once you have the extension in the bolt, then Fi comes very accurately. But if you're using this relationship, find a value close to the actual situation from this table. If you don't have any value, use this value of 0.2. It will be not very far off, but you should be aware of the fact that this is after all a simplification, but it does the job most of the time. Thank you very much.